Hello and welcome to this video on how to assess model fit in confirmatory factor analysis and SEM. My name is Geiser. I'm an instructor with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about multivariate statistical methods including factor analysis and SEM, as well as multi-level analysis, latent class analysis, and topics in psychometrics and measurement. If this is something that interests you, then please consider subscribing to this channel. Also, don't forget to check out the description for additional resources, including workshops that I teach for QuantFish. In this video, I want to address two questions. And the first is, why is model fit assessment important? And then second, how does it work? So how do we assess whether a structural equation or factor model fits our data? How is that done formally? And so here you can see a simple example, a two-factor structural equation model where each factor has two indicators and factor 1 predicts factor 2 in a latent regression analysis. Now, why is it important, first of all, to assess whether this model fits the data? This is important because with our models, we are testing hypotheses about the data structure. And so our models imply a certain structure of our means and or covariances in the population. And we want to make sure that these assumptions that are inherent in the model implications, are not violated by our data. Because if they were, then this would mean that our hypothesis about the model, about how the data are structured or which model generated the data, would be false. So we can falsify a model as long as that model is non-saturated or over-identified, as we say. So if a model has testable restrictions and a model with two factors and four indicators like this one is already over-identified and is testable. And so we can then see whether the model implied means and covariances are in line with our observed means and covariances. Now, why do we care? Well, first of all, we care because we want to test our model. So we want to find out, is this the right model for the data, or do we have to assume a different data structure? And then second, if we didn't test model fit, then we could potentially make an error when we interpret the parameter estimates, such as, for example, the factor loadings or the regression coefficient between factor f1 and factor f2. Those might be biased, and or tests of statistical significance might also be biased if we are basing them off of an incorrectly specified model. So that's a very important issue, and that's why we need to care about model fit assessment, because we don't want to end up with regression coefficients that are incorrect, or loadings or other parameters that are not interpretable and that are misleading. Now, second, how do we do that? How do we assess model fit? What is it based on? And so let's talk about this with a concrete data example. So here you can see the sample means and covariances that I'm using in this example analysis. I have four variables, y1, y2, y3, and y4, and here I have the sample means. So those are the empirical means from the data set. And then also I have the covariance matrix with the variances and covariances of the four variables. Remember that factor analysis and structural equation models are covariance structure models primarily. They also sometimes include or model the mean structure, but primarily the focus of a lot of the SEMs and CFA models is on modeling the covariance structure. And so what we want to do then is, with our model, we want to adequately reproduce the observed covariances and also the observed means. And then that's how we test model fit, is we look at whether the model implied means and the model implied covariance matrix match with our observed data. That's what all model fit assessment is about, is whether there's a discrepancy between the observed means and the model implied means, and between the observed covariances and the model implied covariances. So let's start with a very simplistic model for these data. So first of all, I'm going to fit a single factor model to these data where I have only one factor. And so the idea is that the covariances between those four variables are adequately reproduced by a single factor. So the question is, does this model fit? And what does it look like? How do we assess that? Now with a single factor model, when we take a look at the model implied means and covariances, which you can readily obtain through programs for structural equation modeling, such as Mplus, which are used here in this case, or other programs such as Lavan or JASP or AMIS or Lisrel or something like that. You can get those model estimated or model implied means, as well as the model estimated or model implied covariances. So those are the means and covariances that we would observe or would have observed if our model had fit perfectly in our sample. So the program, so say, figures out what structure is implied by your model and then calculates the means and covariances that this model exactly, so say, is based upon. And now we can compare those to our observed means and covariances that I already showed you. And that's really the key of model fit assessment, is this comparison. Now, obviously, it's relatively difficult to look at every single value and compare every single mean from the observed data to the model implied mean, and also for all the variances and covariances. That would be a lot of work, and it would also be difficult to see whether something is discrepant or not with your eye alone. So one thing that we do then is we look at so-called residuals, or a residual covariance matrix, a residual mean vector, which also is readily calculated by programs for structural equation modeling such as Mplus. So here you can see the residuals for means, and the residuals are simply calculated as the difference observed versus model estimated. And so here you can see they're all 0, indicating that the means are perfectly reproduced by the single factor model. So all of the observed means are perfectly explained or reproduced by our model, meaning there's no model misfit there. So the mean structure is adequately fit by this model. When we look at the covariances, you can see that for the covariances it looks a little bit different, because the covariances here are not fully reproduced. You can see the variances are, so the values on the diagonal, those are the variances, because those are the covariances of the variables with themselves. And this model adequately reproduces all of the variances, so all those residual values are 0. However, the off-diagonal elements of the covariance matrix, which indicate bivariate covariances between different variables, these elements are not all 0. Most of them look like they're close to 0, but there's one here that's 0.31, which you could think, oh, maybe that's also pretty small. But it's hard to say, because those are covariances, they're not standardized. So it's hard to say, is this a significant value? Is this an important value? Is this a covariance that really is not well explained by the model? And so for that reason, because even those residuals in their raw metric are difficult to interpret, programs for structural equation modeling will also give you standardized residuals. And there are different ways to standardize residuals. One is to put those residuals in a correlation metric. And so this is something that I will show you in a little bit, how you can interpret those better. But first of all, one thing that we do to test, so to say, whether overall there's a discrepancy between our model and the data, is we use a so-called chi-square test of model fit. The chi-square test of model fit is an overall test for the null hypothesis that the covariance matrix in the population, sigma, is equal to the model implied covariance matrix, sigma theta. And that at the same time the mean vector in the population, mu, is equal to the model implied mean vector, mu theta. So simultaneously this chi-square test is, so say, an omnibus test for whether all residuals are 0. So all the mean residuals, all the covariance residuals are 0 under the null hypothesis in the population, obviously. And then the alternative hypothesis is that there's a discrepancy between sigma and sigma theta, and or between mu and mu theta. So that would, so say, mean that your model could be rejected if there's a single mean that is not in line with the model implied mean, or if there's a single covariance or variance that is not reproduced by the model. Now, obviously, in your sample, there's sampling error. So the sample will not perfectly reproduce sigma, even if sigma is equal to sigma theta in the population. Your sample covariance matrix S or your sample mean vector may not be equal to the corresponding population sigma covariance matrix and or the population mean vector because of sampling error. And so really what this is about is whether there's a statistically significant difference between them, so they don't have to match exactly in your sample covariances don't have to be exactly equal to the model implied covariances, but they cannot differ beyond sampling error. And so that is tested by the chi-square test of model fit, which is a significance test. So here you can see this test statistic calculated by Mplus for the single factor model, and you can see that the value of the chi-square test statistic is 178.68 with 2 degrees of freedom, and the p-value is 0.00000 something. It's very, very, very small, meaning the null hypothesis is rejected. So what that means is that the model is rejected because the null hypothesis here is that the model is correct in the population, or that the model is the data generating model. And that null hypothesis here can be rejected because the chi-square statistic is significant. So this means the model is incorrect, the model is falsified. And that's, so say, contrary a little bit to how we do significance testing typically, where we are excited when something is significant. It means, oh, we have a significant mean difference if our t-test is significant and there's a group difference and yay, there's an intervention effect. But here, to say, a significant statistic means the model is significantly discrepant from the data. So there's a significant discrepancy between model and data. The model doesn't fit. So that's one thing that confuses many people at the beginning when they first encounter model fit assessment in SEM. They are surprised that a significant result here is often not what you want. However, it is useful because it allows us to falsify incorrect models, to get rid of incorrect models in favor of models that fit the data well. So the chi-square statistic, being an omnibus statistic, does not allow us to really figure out why the model doesn't fit. So right now we found a very large chi-square value that was very significant, indicating that the model totally doesn't fit. However, we have no clue why. The only thing we know is that it cannot come from the means, because we already saw the means. The mean residuals were all 0. So obviously the means were perfectly reproduced by our model. So there was no misfit coming from the mean structure. Also, you may recall that the variances, so the diagonal elements in the residual covariance matrix, the variance residuals were also all 0, indicating that also the variances were perfectly reproduced by our model. So really the misfit must come from some of the covariances, or one actually would be sufficient. And again, we don't know which one. So what's going on? So I told you earlier that raw covariance residuals are difficult to interpret. So when they're non-zero, you don't know. Oftentimes, is that a large residual? Is that an important misfit piece here? So say, is that covariance that is importantly over or underestimated by the model, or is it trivially over or underestimated? And so in order to facilitate the interpretation of residual covariances, we put them in standardized metric. And so one way of standardizing them is by looking at residual correlations rather than residual covariances, because residual correlations are in a familiar metric. We know that correlations can only vary between -1 and +1, and so it's much easier for us to see if something is large or small there than for covariances which are not standardized. So Mplus will also give you residual correlations as part of the residual output, and here you can see that there's one that sticks out, and that's the residual correlation between Y3 and Y4. So that is something that is importantly large. Residual correlation of 0.365 is pretty substantial. So typically, roughly, so say we would say everything that's larger than 0.1 for a residual correlation may be sizable, may be worth investigating. So that is a diagnostic tool that shows us which residuals are large. And so for correlations, that's easier to interpret. So, and then in this case, we would say, okay, the significant chi-square statistic is probably primarily driven by that residual correlation. The other residual correlations are all close to 0. And so we have to look at that part of the model. There's some residual association between Y3 and Y4 that a single factor model does not capture adequately. And so it could be that Y3 and Y4 measure their own factor, or that Y3 and Y4 measure a common specific factor or a method factor. And so therefore, we may consider alternative models that use two factors, or models that use a method factor for Y3 and Y4, or other options. So that would be, so say, then our diagnostic conclusion that there's some residual association between Y3 and Y4 that is inadequately represented by the single factor model. So there's more correlation there than our model explains. Another way to standardize residuals for model fit assessment or model misfit assessment is to use z-scores, which Mplus also does. It also gives you a standardized residual matrix in terms of z-scores. And here you can see that again, this one sticks out between Y3 and Y4. This is a particularly large z-score. You may remember from more basic statistical analysis that a z-score of 1.96 is statistically significant at the 0.05 level for a two-tailed test, and likewise also a z-score of negative 1.96 or smaller than that would be statistically significant at the 0.05 level for a two-tailed test. And so 9.742 is much larger than 1.96, indicating that this is a highly significant residual. You can see that the others here for the covariances also are substantial in terms of their absolute values. However, this one is the one that is largest, and so you would focus on the one that is largest first, because the other ones may go away once you address that issue. So you don't want to address all of the residuals at once, but instead you want to focus on the one that is the largest, and especially if that clearly sticks out like this one, then you want to make sure you address that. So here it's very clear what the problem is, because the data were generated based on a two-factor model, not a one-factor model, and therefore this residual covariance between Y3 and Y4 pops up here, and it needs to be addressed by specifying a model with two factors. So let's take a look at that next. So a two-factor model with two factors that are either correlated or where one factor predicts the other factor would be equivalent models here for these data. So I chose a model where F1 predicts F2, but a model where they're simply correlated would be an equivalent model here that would yield the exact same model fit. So now we have a separate factor for Y1 and Y2 and a separate factor for Y3 and Y4, and F1 predicts F2, so there's a linear association allowed between F1 and F2 in the model, and there's a residual R2 for any variance in F2 that may not be explained by F1. Let's take a look at that model. How does that fit? So the chi-square test, again, that's our omnibus test for testing the entire mean structure and the entire covariance structure for model fit. And you can see that that chi-square value looks much more favorable with a value of 0.165, 1 degree of freedom, and a p-value of 0.6847, which is not statistically significant at the 0.05 level. So this model is not rejected according to the chi-square test. In other words, it fits the data very well. When we take a look at the sample and model implied covariances, you can see that now this covariance that was previously problematic here, this one is now exactly reproduced by the model, because it is the exact same in the sample covariance matrix and the model estimated covariance matrix. So there's no more problem there, because this covariance is now exactly reproduced. Also, you can see that the other ones are all close. It's a little bit hard to see again because this is not standardized, but you can see that the values here off diagonal are pretty similar to those off diagonal values here. So there isn't any misfit, as was indicated by the overall chi-square test, which looked very good. Now, when we look at the residuals for this covariance matrix, then we can see that obviously this previously problematic residual covariance is now 0. There's a 0 residual for that because it's exactly reproduced. So there's no more problem there in terms of model misfit. This model fits the data very well, and so we could now safely interpret the parameter estimates of this two-factor model, and that shouldn't have any bias. Now, this model could still be wrong, because it could be that rather than F1 being the cause of F2, it could be that F2 is the cause of F1. So this model not being rejected by the chi-square test does not mean that this is the true model. There are alternative models that may fit the data equally well or even better. It just means this model is not ruled out. This has not been falsified. So this model may be a correct model. It doesn't show misfit, but there may be other reasons to prefer a different model other than based on those fit statistics. Now, there are other or additional ways to assess model fit. One is when you have multiple models and when the models are nested, you can use so-called nested model chi-square tests. I have a separate video on this channel on how to do that, so feel free to check that out as well. Also, you can use information criteria for a more descriptive comparison of different models that may or may not be nested. So those information criteria could also be used to compare non-nested models, and commonly used ones are the ACAICS information criterion or the Bayesian information criterion, AIC and BIC. Furthermore, there are so-called approximate or closeness of fit indices that are also often used in model fit assessment. I personally find them to be more problematic because they tend to be less sensitive to model misspecifications as the sample size increases, which is counterintuitive. You would think that a test statistic should be more sensitive to misspecifications with larger samples, and that is the case for the chi-square test of model fit. So the chi-square test becomes increasingly sensitive to model misspecifications with increasing sample size, whereas those indices that I'm going to show you now do not, but I'm going to cover them here briefly because they are also frequently used. So one commonly used one is the root mean square error of approximation, RMSEA, which is an approximate fit index where values smaller than or equal to 0.05 are commonly seen as indicating adequate model fit. There are also comparative fit indices that compare the model that you specify to a target or null model, so a baseline model, so the target model is your model, and the CFI and TLI compare your target model to a baseline or null model that postulates that there are no covariances between the variables. And so those indices should take on values greater than or equal to 0.95, I guess. So we would then see them as being adequate when those values are close to 1. And I have a separate video in which I explain in detail how the CFI and TLI work in terms of their underlying mathematics. And then finally, there is an index called the standardized root mean square residual, which is a summary measure of the standardized correlation residuals. And so for that, we like to see a value that is 0.05 or smaller, which would indicate that the average correlation residual is not very sizable. And that's maybe one of the more useful indices in my opinion, because at least that has a meaning to it in terms of its value, because we know again that residual correlation that is 0.1 or greater is somewhat large, and then 0.05 we would say, yeah, that's really small. So if the average residual is 0.05 or smaller, then that may indicate that the model is not bad. I hope you found this video useful to learn more about how model fit assessment is done in confirmatory factor analysis and SEM. If you did, then please consider subscribing to this channel. Don't forget to check out the description for additional resources, and I'll see you next time.